In this tab, we have temperature and cost data. And the question is asking us, can you use the average outside temperature to predict the cost to heat a home? Anytime you see predict, you know you're running regression. So we're trying to find out if we can use the temperature to predict the cost to heat the home. So I've gone ahead and run that regression, and because there's only one variable, you only need to run the regression once. Now the first thing you look at is the overall global p-value, and that's under the significance f. If that's less than 0.05 or 5%, then it's significant. And remember, 5% is the chance that you're wrong, and you want that to be small. You want the chance that you're right to be 95%, to be really big, and the chance that you're wrong, or that this data kind of came together as a fluke, to be very, very small. That's why we're looking for numbers that are less than 0.05. So if you've looked at the global p-value, then you know that it is significant, because anytime you have e to the negative, in this case 0.8, means you'd move the decimal places to the left 8, the decimal point to the left 8 places. Then you look at the actual p-value for the variable. In this case, our variable is temperature, and we can see the p-value is very, very small. In fact, that's the same because we're running simple linear regression. When you have one variable, the global value and the individual value will always match. Okay, so let's go down to the questions so we can interpret what this means. The first one says, is temperature a significant predictor of cost? If the p-value is less than 0.05 or 5%, feel free to turn it into a percentage if you'd like. So if it's less than 0.05, this one says it's 0, and I'll increase the decimal places so you can see. Really, really small. Yes, it is significant. The chance that we're wrong is very, very small. Now, the whole point of doing this is saying, okay, I have these temperatures and I have these costs. I have all this information from the past. How do I use that to predict something in the future? So what if the temperature is 70 degrees? This is the whole point of doing regression. I want to be able to predict a number. And I've gone ahead and graphed this data in a scatter plot, and I've put in the line of best fit. And as you can see, if it's 70 degrees, if we follow this line out, we assume it's probably going to be somewhere around, what, $50 to heat the home? Okay, that makes sense. And the next one says, what if the temperature is 5 degrees? Well, if it's 5 degrees, we assume it's going to be somewhere around, I don't know, $350. This is our estimation. Now let's go ahead and plug in the formula. So we know the formula. We take the intercept, and we are going to add to that the coefficient of the temperature multiplied by the value of the temperature. And what is the value of the temperature? Well, we're telling you it's 70 degrees. So multiply that by 70. And I get 49.51. We estimated it was going to be 50 from the line. Yeah, that's pretty darn close. And you want to know why? Okay, way back in Module 6, do you remember making graphs and we said put in the line of best fit and then make sure you put the regression equation with it? Look at the regression equation. Y equals 367.29. That's our coefficient, our intercept. And we're taking that negative 4.5397 times x. Here's our coefficient for the temperature, and we're multiplying it by our variable, which is 70 degrees. So, multiple modules ago, you already had the answers. This is how it all comes together. So let's do it for the 5 degrees too. So we're going to take the intercept, and we're going to add to that 5 times, so the value times the coefficient. And we get $344. I think we had estimated $350-ish. Pretty darn close. Here's what it really would be. Okay, now what if the temperature is 0? Well, we can use the line, and we know when the temperature is 0, that's where it crosses the y-axis. That's why we call it the y-intercept. That's where it crosses the y-axis. And when it's 0, we expect it to be 360, 70 something. How do we figure that out for sure? Well, let's take this time, let's delete this. Let's take the intercept, And we're going to add to that 0 times the coefficient of the temperature. Now, what happens when you multiply anything by 0? You get 0. So if your variable is 0, then when it crosses the y-intercept, it's going to be whatever this coefficient is right here. So it's 367. Essentially, you're saying, ignore the x's. Pretend they don't exist. What do we think the temperature, or what do we think the cost is going to be? All right, here's the next one. If the temperature goes up by 1 degree, what happens to cost? So let's see. We have the intercept. If the temperature goes up by 1 degree, so our value is 1, let's multiply that by the temperature coefficient. So for every degree this goes up, we're multiplying that by negative 4.54 approximately. So all this means is every time the temperature goes up by 1 degree, the cost is actually going to go down by $4.54 because this is a negative number. So it's just simple math. This part is going to equal whatever this temperature is because you're multiplying, or this coefficient is because you're multiplying by 1. If we multiplied by 2 degrees, it would be double that, approximately $9. So for every degree the temperature goes up, the cost goes down by $4.54. In this case for a grand total of $362, so it took it from $367 to $362. All right, now it says, how much of an impact in prediction does temperature have on heating costs? Well, we know it has some sort of impact. It's significant because the p-value is less than 0.05. We've determined that already. But how much of an impact does it actually make? All right, it's not necessarily causing it, but on this prediction, how much of an impact is it going to make? And that simply, for a simple linear regression, is your r-squared value. And these are percentages. So 68% of the change in a heating cost in a home is due to temperature. That's what this says. Now, that means there are other things that can help explain the rest of it, and that's where multiple linear regression comes in. But in this case, we're just talking about temperature. So that's the impact that temperature has on cost. Now, what is the average distance between the predicted cost and the actual cost? So we're saying, hey, if it's 70 degrees, what do we think the cost is actually going to be? Well, we think it's going to be, we calculated this already, $49.51. But will it be exactly that? No, because there are other things that might impact the cost. And so what is the difference? What's the error we might have? That's our standard error. On average, how much error are our predicted values likely to have? Same thing, just said in a different way. That's our standard error. So how much error is expected to be in here? And the one above is what's the distance? So between this point and this line, what is that average distance? And this point and that line, all right? So on average, how far away from the points are the lines? It's the same thing, same value.